Hi, my name is Madeline Crabtree. The date is January 14th, 2020. And this is my presentation on Case Connection Unit 4. So in Case 1, there's a newborn girl that develops lethargy, hypothermia, and apnea 24 hours after birth. And based on the lab panels the doctor ordered, the cause of this newborn symptoms could be distinguished between a urea cycle disorder or a beta oxidation disorder. So now in a urea cycle disorder, it's a hereditary metabolic disorder, and it occurs when there's a deficiency of one of the enzymes in the urea cycle that's responsible for removing ammonia from the bloodstream. Now, this is a genetic mutation, and it causes a defect in the metabolism of the extra nitrogen that's produced by protein catabolism. So when there's a deficiency in one of the enzymes, CPSI, OTC, ASS, or ASL, or the cofactor NAGS, it results in an accumulation of ammonia. And this means that the infants will rapidly develop lethargy, hypothermia, and anemia. Now, in a beta oxidation disorder, this is a very rare inborn error of metabolism, and is most commonly due to a deficiency in the medium chain acyl coenzyme A dehydrogenase, or MCAD. And in the mitochondria is where there is beta oxidation by the enzymes. So MCADs are going to oxidize medium length fatty acids, where VLCADs, which are very long chains, will oxidize very long fatty acids. So in infants and young children, the fatty acids are oxidized 12 hours after fasting, and the fatty acid oxidation deficiency is going to be in the form of fasting hypoglycemia. There's also going to be no increase in the serum ketones. So out of the diagnostics, blood glucose, urinary acids, serum fatty acids, and plasma glutamine, only one can be used to distinguish between a urea cycle disorder and a beta oxidation disorder. So first, for the blood glucose, in a urea cycle defect, there would be normal levels, whereas a beta oxidation defect would have low blood glucose. So glucose levels don't really have an association with either disorder, so it wouldn't work to distinguish between the two. So for urinary acids, they are specific to the urea cycle and not beta oxidation. Thus, there would be no way to distinguish between the two disorders. So in a urea cycle defect, there is a defect in the ornithine translocase, or OTC, and this causes ureagenesis and orotic aciduria because there's a decreased amount of OTC in the mitochondria. That then means there's going to be an accumulation in the cytoplasm. So because there's an overabundance of carbamyl phosphate, it's going to spill into the pyrimidine biosynthetic system, and there's going to be an increased amount of orotic acid produced. So this newborn child shows increased levels of orotic acid. So this is an indication that the OTC enzyme is deficient, whereas the carbamyl phosphate is not impaired. Going further, the serum fatty acids are specific to beta oxidation. And as discussed previously, the MCAD or the VLCAD are enzymes that are missing. So this would cause an accumulation of fatty acids in the body tissues. And this gives us further insight into a beta oxidation disorder, but it's not a way of distinguishing between the two disorders of beta oxidation and urea cycle. And lastly, there's plasma glutamine. And plasma glutamine is a non-toxic and non-essential amino acid that detoxifies and transports ammonia. So in a urea cycle disorder, plasma glutamine levels are raised, and in a beta oxidation disorder, plasma glutamine levels are normal. So as discussed previously, the young child has increased amounts of ammonia in her blood, and it's the same symptoms that's being shown here when there's a urea cycle disorder. So the plasma glutamine is the best diagnostic to use to distinguish between the two disorders. Now moving on to case 2. Case 2 is a newborn girl presents a sign of phenylketonuria, or PKU. Now phenylketonuria, or PKU, is an inherited disorder that increases the levels of phenylalanine in the blood. And babies that are born to mothers who have PKU or mothers that have uncontrolled phenylalanine levels can pass on PKU to their babies. So phenylalanine is an amino acid that's used as a building block for proteins, and it's obtained through the diet. So causes of PKU occurs in the mutations in the phenylalanine gene, And this phenylalanine gene provides instructions for making phenylalanine hydroxylase. And this enzyme is required for the conversion of phenylalanine to tyrosine. So when there's a gene mutation, it's going to reduce the activity of the phenylalanine hydroxylase. And that means that there's the phenylalanine from the diet is not processed effectively. So the phenylalanine can build up in the blood and become actually very toxic. And in the brain, the nerve cells are very sensitive to phenylalanine levels, so excess amounts of phenylalanine can cause brain damage. So going back to the phenylalanine hydroxylase, because this is required for the conversion of phenylalanine to tyrosine, when the phenylalanine is potentially deficient, the tyrosine actually becomes the more essential amino acid. So when there is a BH4 loading test done, the BH4 is an essential coenzyme for the conversion reaction of phenylalanine to tyrosine. So in patient 1, the levels of phenylalanine are elevated after there's BH4 intaken. And the levels of elevation show that the patient cannot metabolize the amino acid and convert it to tyrosine. For patient 2, the levels of phenylalanine fell, which indicates phenylalanine was converted to tyrosine. So these results show that PKU is not the proper diagnosis, but perhaps it's tetrahydrobiopterin deficiency phenylalanemia. This is a BH4 deficiency that has similar PKU symptoms, but is not the same. Thank you.